Space Explorers, welcome back. All right, so today's objective is to finish Chapter 4, and to do so, all we need to cover is interplanetary flight, or in other words, how to go from one planet up to another planet, okay? And the methodology we're going to employ here is very straightforward and simple, and yet this is what is used in practice, in industry, academia, and other organizations throughout the world, and that is the method known as patched conic, okay? So patched conic method assumes that the spacecraft is only under the gravitational influence of one primary body throughout the interplanetary flight. Starting, say, if you're talking about an Earth-Mars flight, then we're going to first assume that the spacecraft is under the influence of the Earth only. Then we'll apply a delta V maneuver that will transfer itself from what's known as a parking orbit around the Earth up onto an hyperbolic transfer trajectory that will then lead the spacecraft to exit the sphere of influence in terms of gravitational attraction of the Earth. And then the spacecraft will then keep coasting for a long period of time under the gravitational influence of the Sun only. And then whenever the spacecraft will get closer to the target planet, Mars in this example, then it's going to be pulled by Mars' gravitational attraction and forget about the Sun at that point on, okay? So the methodology of kind of patching those different trajectories together from the hyperbolic departure orbit to leave the Earth influence to the elliptical transfer orbit around the Sun, and then patching at the end of this elliptical transfer orbit another hyperbolic, this time capture orbit around the target planet, is the methodology known as patched conic, okay? So this is all in 4.5. Interplanetary flight. Yes. I know you guys have been waiting for this section for a long time, but as a heads up, it is not that exciting because it gets to be very, very simple, okay? I'm assuming that you like when things get quite complex and mathematically involving. That's not going to be the case here. So maybe if math is not your thing, you'll find that section very interesting because it is so simple. My taste is that I prefer complex derivations and things like that, but that will come in Chapter 5. And this is why Chapter 5 is my favorite one, because it brings back notions we previously seen in Chapter 1. Vector C's, cross product, skew-symmetric matrices, rotation matrices, and all of that good stuff will come back and haunt us in Chapter 5, and that's why I like it so much. But for the time being, again, we're going to look at things from a simplistic point of view, and even to analyze interplanetary flight, this is what is being done in most organizations throughout the world. Okay. But before we can actually look at the mechanics of going from a planet to another one, we have to look at something known as the sphere of influence. Because within the patched conic method I've just described, we need to know when to switch the gravitational influence of the home planet off, and then switch the gravitational influence of the Sun on. And then we're going to leave that gravitational pull on for a long period of time throughout the interplanetary transfer along the elliptical orbit. And then when we're going to get closer to the target planet, we're going to switch the gravitational pull from that planet on. So we need to know at what point are we going to pull the trigger and switch from one gravitational field from another one. And to do that, we're going to need to look at sphere of influence, which is defined by its radius in terms of gravitational attraction activity. So if this is, say, your home planet, Earth, then Earth will attract any objects in its vicinity up to a certain point, okay? And that certain point is going to be quantified through the radius of a sphere enclosing the planet, and that sphere is known as sphere of influence, okay? So we're going to say that Earth would have a gravitational activity whenever an object is within this sphere of influence, and outside of it, we'll consider the spacecraft or any object to be under the influence of the sun only. So the norm of this radius vector for the radius of the sphere of influence is denoted by RSOI for sphere of influence. And it's going to be quantified by D, which D is the distance between Mr. Sunshine, always happy, and the planet for which you are calculating the sphere of influence. This is the sphere of influence, red, and this is D. D is the sun-planet distance over the mass of the planet, MP, or times the mass of the planet, MP, over the mass of the sun, and the sun shall be denoted by this symbol, subscript, so a circle with a dot inside of it. And you're going to take all this to the power 2 over 5, okay? So this is mass of the sun right here. So this distance corresponds to the distance at which both gravitational attraction are exactly equal to each other, okay? So the gravitational attraction from the planet being equal to the gravitational attraction of the sun is exactly at RSOI. So our objective to do an interplanetary flight will be to, again, start in a circular low Earth orbit, denoted or referred to as a parking orbit, and then apply a delta V maneuver to go from the circular orbit to a hyperbolic departure orbit, such that we will effectively escape the gravitational attraction of the Earth. So we're going to go past its sphere of influence, and what we want to have is some net residual velocity, because we don't want to be ending up at zero velocity and be standing still. So objective is to get a hyperbolic excess speed, such that this excess speed is large enough to kick ourselves into a big elliptical transfer orbit between planet 1 and planet 2, and then reach planet 2 just by coasting without applying any further delta V maneuver. So for an interplanetary flight, there's going to be 2 delta V maneuvers involved. One to go from the low Earth parking orbit to the hyperbolic departure trajectory, and this delta V maneuver is going to be sized accordingly to end up with a hyperbolic excess velocity, V infinity departure, which is great enough to reach planet 2 by freely coasting. And then whenever we want to reach our target planet, or planet 2, we'll apply another burn to kick ourselves from the hyperbolic arrival orbit down to a capture orbit and remain on orbit around the target planet, if that's what we want, okay? So let's have a look at the different steps involved in doing that kind of analysis. And that will be in section 4.5.2, which is the patch conic method itself. Four point 5.2 patch conic method. Because we are patching conic sections together, or different orbits and trajectories together from the hyperbolic trajectory, we're going to patch the end of that trajectory to an elliptical transfer orbit around the sun, and then patch this elliptical transfer orbit to another hyperbolic trajectory upon arrival at the target planet. Hence the name patched conic. Okay? So, what's going to happen? I'm going to leave my drawing here for the remaining of that section, I believe, because I'm going to refer extensively to it. So if you look at the sun, planet 1, planet 2 perspective, like this, if this is planet 1, we'll consider that all planets within our solar system lie exactly in the same plane, okay? And furthermore, we will assume that their orbits are all circular, which kind of goes against Kepler's first law, which was that all planets follow elliptical orbits around the sun. But if you look at the actual eccentricity value for those orbits, they are all pretty low. So for all practical purposes, we're going to consider that the orbits of all planets around the sun are perfectly circular. And this, you'll have to assume that this is a perfect circle, obviously, which doesn't look like one, thanks to my artistic skills in terms of drawing. So the way it's going to work again is that you want to go from one planet, and then for this demonstration, we're going to go from a low, from an inner planet to an outer planet. We're going to go to a planet that has an orbit bigger than the original one. Show properly? Yes. Okay. So let's switch to blue. So the way we're going to do things is from the sun's perspective, because the sphere of influence are so small compared to the grand scheme of things. And if you look at the actual numbers, and I gave you the numbers for the sphere of influence of all planets within our solar system in terms of astronomical unit and fraction of. One astronomical unit is the distance from the sun to the Earth. And for example, if you were to look at the Earth's sphere of influence in terms of radius, it is 0.006. So just a tiny fraction of this big distance is what defines the sphere of influence of Earth here. Okay? So because of that, for all practical purposes, we'll consider that we're starting exactly at the planet here and ending up exactly at the target planet upon arrival. And we're going to do that by doing a simple Hohmann transfer between planet 1 and planet 2. Okay, so all we're doing is to go from here and then elliptical transfer orbit and then reach planet 2. So this is from the sun's perspective, or this is the heliocentric transfer orbit. Helio for sun, centric at the center of the system. And what we're doing here from this perspective is just half of an elliptical orbit to go from planet 1 to planet 2. So because we saw Hohmann transfers previously in that chapter, we know how to do that. But there's one other thing to consider here, and that is the timing. Because we just don't want to reach planet 2 orbit, but we want to reach planet 2 itself. So whenever we're going to launch from planet 1, we need to ensure that planet 2 has some position with respect to, or in terms of angle here, such that when we launch from planet 1, planet 2 is around here, and then planet 2 throughout our transfer orbit will have to advance its orbital position in terms of angle to go from here all the way to here, such that when the spacecraft arrives at the apogee of its heliocentric transfer orbit, then it's going to meet planet 2 exactly at that point and not miss it. Because if you miss planet 2 here, well, I mean, that's not too good, right? That was the intent, to go from one planet to the other one. So we need to time things properly to ensure that planet 2 advances its orbital position in terms of angle by a given amount based on the fact, or based on the heliocentric transfer orbit dimension. Okay? So we're going to look at that first. So this angle that planet 2 needs to have with respect to planet 1 upon departure is going to be denoted by phi. and will be referred to as our phasing angle, okay? And the amount that planet 2 has to cover during the time spent on the heliocentric elliptical transfer orbit is going to be denoted by phi subscript circle x. We're going to use subscript circle x whenever we talk about target planet, because that kind of denotes a target, essentially. So this is a target planet in terms of what it needs to cover during the time that the spacecraft spans along this transfer orbit, such that the spacecraft and planet 2 meet up upon arrival at the apogee of the transfer orbit. Okay? So again, the angle the planet must cover is going to be equal to pi minus that minus the angle that the planet 2 had with respect to planet 1 when the spacecraft launches from planet 1, known as the phasing angle, like that. Okay? So that's one equation that we're going to keep in our back pocket. Now, let's have a look at the time that the spacecraft needs to spend during the transfer to make sure that the meetup point is actually satisfied with planet 2 at the arrival. Okay? So we're going to say that this amount of radiance needs to be covered in an amount of time referred to as T transfer, where T transfer is simply half of the orbital period of the green orbit, so half of the elliptical orbital period, essentially. And that is going to be equal to pi times square root of semi-major axis of this elliptical transfer orbit cube over mu. Now here, because we're doing things with respect to the sun's perspective or the heliocentric system, we're considering that the spacecraft is under the influence of the sun's gravity throughout the travel, and therefore we need to use mu of the sun, denoted by the circle with the dot in the middle. Okay? Nice. Or we could also say that this angle, phi, that needs to be covered by planet 2 in terms of radiance would be equal to the mean orbital motion of planet 2 in radians per second times this time here, which is T transfer. Because the mean motion in terms of angular rate that the planet 2 sweeps its orbit times the time spent for the spacecraft on this half orbit here, which is T transfer, will give us the remaining angle that the planet 2 needs to cover in that amount of time. Okay? Or in other words, mean orbital motion of planet 2 times pi times square root of semi-major axis of the transfer orbit, which is the elliptical orbit in green, over mu of the sun. So this is this angle here. Where, by the way, if you need to calculate things with numbers, this can also be written as square root of mu sun over the distance between the sun and planet 2, denoted by r with the x symbol like that, over cube, and times pi, and times semi-major axis of the elliptical transfer orbit over mu of the sun, like this. Okay? Now you may say, okay, well, I know mu of the sun, it's probably given in the lecture notes, and it is in chapter 2 with the table for gravitational parameters for all bodies in our solar system. Mu of the sun is there. The radius between the sun and all planets within our solar system are provided in this chapter, specifically in table 4.2. This is the heliocentric radius, or the radius from the sun to all planets within our solar system. So we have this, but how can we determine the semi-major axis of our elliptical transfer orbit taking us from planet 1 to planet 2? Well, that's not very difficult, because you will remember that the semi-major axis of an ellipse is its perigee distance plus apogee distance divided by 2. And turns out that the perigee distance will be the distance from sun to a planet, and the apogee distance of the transfer orbit in green will be the sun planet 2 distance, such that you could say where AT is actually radius in this example of the sun Earth, like that, plus the radius of sun target planet divided by 2. As simple as that. So as long as you know your home planet and the target planet you want to go to, you can easily figure out the semi-major axis of this elliptical transfer orbit. You know mu of the sun, and because you've been able to calculate semi-major axis of the elliptical transfer orbit, it means that you know the sun home planet distance, which is this, home target planet distance from the sun to the target planet, which is r with the x, to get this angle that you need to shoot for, or that the planet 2 needs to cover in that amount of time. Okay? So essentially what you need to figure out to launch and to determine the launch window to leave planet 1 is phasing angle again, which can be obtained by equating this expression with the other one we had. And that was just pi minus this. Okay, so if you equate both expressions for the angle that planet 2 needs to cover in that amount of time, let's say n this times t transfer, and t transfer, remember that this is half of the complete orbital period in the transfer orbit, has to be equal to pi minus phasing angle such that you could say that the phasing angle between your planet and the target planet at launch time will be equal to pi minus mean orbital motion of the target planet times time spent during the transfer, where the time spent during the transfer was calculated just before, so we could sub it back into here and then figure out the geometry between both planets at the time at which you're going to launch from planet 1 to reach planet 2 eventually. Okay? And that is assuming that all you do is one delta V maneuver here, kick yourself onto the hyperbolic departure orbit that will then freely drift you onto this elliptical transfer orbit and then eventually reach planet 2 without any other delta V maneuvers throughout the way. Okay. So now that the timing aspect has been figured out, let's try to see how much fuel is going to be needed to go from planet 1 to planet 2. This is the initial orbit, and then the heliocentric elliptical transfer orbit connecting planet 2 to planet 1 around Mr. Sunshine. Okay? So let's focus on the hyperbolic, not transfer, but departure orbit. Because there is only one transfer orbit in the entire system here, and that is the heliocentric elliptical transfer orbit. The hyperbolic departure orbit is the one that we're going to connect to the elliptical orbit here, to the patch conic philosophy. Okay. So to analyze what's going to happen at departure, the very first step you need to figure out is the speed at which planet 1 is traveling around the sun. And whenever we're going to look at speed with respect to the sun's perspective or with respect to this system, and it's zoomed out, where we see both planets and the sun in the middle, I'm going to denote the speed there with the capital V's, okay? So I'm going to say that this planet happens to coast along its circular orbit around the sun and therefore has a speed denoted by capital V D. Okay? Now this capital VD also happens to be the speed at the perigee of the elliptical heliocentric transfer orbit. Sorry, no, that's not what it is. Well, so VD is not this. V, let's call it planet 1. Okay, in the notes I've used the notation for Earth, but to make things a bit more general, I'm going to say planet 1. So the speed that planet 1 has along its circular orbit around the sun is simply V1 equals square root of mu. Mu of what? Well, look at that system here. This is the sun that's pulling planet 1 along an orbit around itself. So I'm going to use mu of the sun over the radius between the sun and planet 1. R1, like that. But if the spacecraft is orbiting here around the planet, we will assume that from that perspective, the spacecraft has the same amount of speed than the planet, okay? So it's kind of split together or orbiting around. But from this grand scheme of things, we're assuming that the spacecraft has the same speed. But that's not enough to go from here to here, because what we want is to have a larger velocity that's going to correspond to the speed along this transfer orbit at its perigee. And this is going to be denoted by VD. All right, so this is the same as the first few orbital maneuvers we've looked at in this chapter, where we were going from circular orbit to a larger elliptical orbit. So this is exactly the same. If I'm using a different nomenclature for the variables, but that's the same idea. So VD is going to be larger than V1, and is going to be obtained by the vis-viva equation applied at the perigee of this big elliptical transfer orbit. So again, this is around the sun, so mu sun times 2 over r times 1 over a. R, what is this r? Well, this happens to be the distance between the sun and the perigee, the transfer orbit. Is going to be the same as R1. And semi-major axis of what? Well, semi-major axis of the only elliptical orbit involved in this entire transfer, which is the transfer orbit. And we'll say A, transfer orbit, which again is only obtained by R1 plus R2, which is sun planet to distance, divided by 2. Okay? Such that the difference in those two speeds will give you the speed that the spacecraft needs to have in excess of the planet speed around the sun. And this will be denoted by, let's use another color, because those two speeds were with respect to the sun. But now it means that the spacecraft needs to travel faster than the planet itself, or needs to have a speed with respect to the planet's point of view to be equal to v infinity, which is going to correspond to the hyperbolic excess speed, which is going to be exactly equal to the speed at this point along the elliptical transfer orbit, Vd, minus V1. Let's put them in green to be consistent here with the color scheme. Vd minus V1 will give you V infinity with respect to planet 1, okay? And this is known as the hyperbolic excess speed with respect to the planet, okay? So this is the speed that the spacecraft will have yeah, it's right here. Whenever it would exit the sphere of influence of planet 1. So now I'm zooming in what's happening here, and I'm forgetting about the sun, only looking at planet 1. Planet 1 has its sphere of influence quantified to r SOI. Originally, we're starting the process from a low Earth parking orbit, which is a circular orbit like this. And then we're going to apply a delta V maneuver to increase the energy quite a bit, to go, say, from here into a hyperbolic trajectory that would get us outside of the sphere of influence of planet 1. So the speed that we're going to reach whenever the distance between planet 1 and the spacecraft reaches infinity, which is at the limit of the sphere of influence, by the way, because from that perspective, the sphere of influence is very large with the dimensions involved here. But this is contrarily to what I said here, where the sphere of influence from that perspective is very small, but yet here it's very large. So this is whenever r is equal to infinity between planet 1 and our spacecraft upon exiting the sphere of influence. This is the hyperbolic excess speed we're going to have here, and that is from the planet's perspective. Okay? So essentially think of it as doing a regular Holman transfer from the heliocentric perspective and finding what I call a fake delta V, which is the difference in speed between the speed along the ellipse at its perigee and the speed along the circle here, and that is your V infinity. So this is almost like a fake delta V, and why I call it fake is because there's no delta V maneuver applied here, right? The delta V maneuver is not applied here, but actually the only delta V maneuver in the entire system is delta V departure that takes us from the circular orbit up to a hyperbolic orbit that will be sized such that the speed the spacecraft would have along this hyperbolic orbit whenever r reaches infinity exactly matches the difference in heliocentric speeds calculated from this perspective. And that is the key thing to analyze interplanetary flight, okay? Always begin with the heliocentric system, figure out the normal geometry, which speed is greater than the other one, and assume that you do a delta V between those two speeds here and call it V infinity, which is the speed that the spacecraft needs to have in excess to the planet's speed around the sun, okay? And now that you figure out the excess speed along the hyperbolic orbit here that is being patched to this elliptical transfer orbit, hence the name patched conic method, is going to be used to size this hyperbolic trajectory accordingly, which is what's going to happen next. Okay? So we need to determine the semi-major axis of this hyperbolic departure orbit. Semi-major axis of the departure hyperbolic orbit. Why hyperbolic orbit? Because this is the only way we can escape a planet's gravitational attraction, right? So we need to do a hyperbolic orbit with respect to the planet, but that turns out to be eventually an elliptical orbit, which is a close orbit around the sun, because we don't want to escape the sun's orbit or the sun's influence, okay? From this perspective, we want to stay in a close orbit around the sun. We don't want to escape the solar system by embarking onto a hyperbolic trajectory from that perspective. That's not the intent. Okay? So AD, which is, again, the size, if you will, of this hyperbolic departure orbit that allows us to escape the sphere of influence of planet 1, is actually directly related to the hyperbolic excess speed by minus mu of planet 1. Call it mu1 over the excess hyperbolic speed square with respect to planet 1. Okay, so you take this value you got by doing a fake delta V from the heliocentric system perspective. So the speed along the big elliptical transfer orbit minus the speed of planet 1 along its circular orbit gave you the hyperbolic excess speed here. Plug this back into this relationship by squaring it, and that's going to give you the semi-major axis of this hyperbolic trajectory or orbit. And now, knowing that the actual delta V maneuver takes us from this parking orbit to this hyperbolic trajectory, then we need to figure out the speed along this hyperbolic trajectory, specifically at its perigee, because the point at which we're going to apply the maneuver along the blue Leo parking orbit around planet 1 will turn out to become the perigee, the hyperbolic transfer orbit, and the speed at that point, so V of the departure orbit, so this is the speed of hyperbolic orbit at its perigee, which is the point of application of the actual delta V maneuver, will just be equal to this viva. Now mu, we're not looking at the sun's perspective or the heliocentric perspective anymore. Everything we do now is focused from the planet perspective. So I'm going to use U of planet 1 times 2 over R minus 1 over A. A of what? Well, A of this hyperbolic orbit. So A D, this. And R happens to be the distance between the radius of this lower parking orbit and the center of planet 1. That we will denote by R of the parking circular orbit, like this. So R parking, and to simplify things for you, I'm going to write this one in blue because this is quantifying the size of the Leo parking orbit, like that. So now you have determined the speed at that point along the big hyperbolic orbit. Now, if you want to know the actual delta V maneuver in terms of its size, you need to also figure out the speed along the parking orbit, and that is quite simple. So that would be the speed V along any point of the parking orbit, which happens to be a circle, the square root of mu of the sun or mu of the planet, while the parking orbit is around the planet. So you better use the planet's gravitational parameter mu1 over r, and r is r parking. So the distance between the planet and the LEO circular parking orbit, like that. Which one of these two will be the greatest between V along the high energy hyperbolic transfer orbit, or not transfer, but hyperbolic trajectory, taking us away from the sphere of influence of planet 1, and the speed along the small bounded circular orbit? Well, obviously this one is going to be much greater than that one, so ultimately we're going to write that the actual burn maneuver, delta V departure, will be equal to V along the hyperbolic departure orbit at its perigee, and minus the speed along the lower parking orbit around M1. And that will be your answer for the actual magnitude of the only thrust maneuver that you need to apply to go from parking onto this hyperbolic trajectory that has an excess speed sufficient to take us from planet 1 onto this big elliptical transfer orbit around the sun. Okay? This is where the only maneuver takes place to escape planet 1. Now, if you don't do anything, you will eventually reach planet 2 along its orbit, assuming that you timed the departure at the proper phasing angle, as we've discussed previously in this lecture. So you're going to reach planet 2 along its orbit, but then you're going to keep coasting along the transfer orbit forever. If you don't apply any other maneuvers here, that's what's going to happen. So if you want to put yourself onto an orbit around planet 2 and stay there, which is a typical situation, you need to apply a second delta V maneuver. Okay? That second delta V maneuver is known as the capture maneuver upon arrival. But first we need to figure out, with respect to planet 2 that I'm going to draw in red. Planet 1 was blue, pretending that that was the Earth. Planet 2 could be Mars. So this is planet 2. If the objective is to put yourself onto a circular capture orbit around planet 2, you will arrive along a hyperbolic trajectory with respect to the planet, and you will enter the sphere of influence of planet 2. So why planet 2? With some velocity that we're going to denote V infinity, this time with respect to planet 2. Okay? Now this is going to be obtained exactly as before. So going back to our heliocentric perspective and analyzing the speed involved, this time not at departure from planet 1, but at arrival at planet 2. So planet 2 itself is coasting along a circular orbit around the sun like that, and we are coming in with a speed along this elliptical transfer orbit in the same direction, like this. Capital V that I've denoted is A for arrival along the transfer orbit, this time at its apogee. So V infinity that you would have with respect to the planet upon entering its sphere of influence would be equal to V2 minus VA, simply. Okay? And then from this, you could do the exact same thing as before, and that is to relate this V infinity of this hyperbolic arrival trajectory to its semi-major axis, and then to its speed at the perigee of this hyperbolic trajectory to figure out the delta V needed to slow you down to enter a capture orbit. Okay? So now that you've determined V2 and VA from this perspective, you go back to the planet and then get the speed. VA, which is speed of hyperbolic trajectory of arrival, hyperbolic trajectory at its perigee. And you'll remember that this could be related directly to V infinity. So you could write square root of V infinity at planet 2 square plus 2 mu of planet 2, 2 mu 2, over R, and R is going to be our capture, which is the radius of this circular capture orbit. Our capture. Okay? So this is how you could relate V infinity to the speed, which I'm going to use a small letter because this is the speed from that perspective, right? The capital V's were from the speeds from the heliocentric perspective, but now we're shifting the focus to planet perspective. So this is what you would get. And as before, you also have V capture. As before was V parking. V capture is simply the speed along a circular orbit around planet 2 that has a radius of R capture, like that. Okay? So that would give you then the delta V needed to slow you down from VA, which is a high speed because you are coasting along a high energy orbit, down to a bounded low energy capture orbit, and that would give you something positive. So that is the delta V needed to remain on orbit around planet 2. Now, what would happen if no other delta V's would be applied? Then it depends on the situation. Okay? So let's have a look at what would happen if no other delta V's are applied at the target orbit, such that you end up on a flyby trajectory. And that could lead to the well-known slingshot maneuver you've heard in some movies, probably. Okay, so flyby trajectories upon arrival at the target planet. Are those generated if no delta V is applied at target planet, which was our planet 2 in this previous discussion, okay? So you have two situations. If you go from a low orbit planet to a high orbit planet, right? This is planet 1, this is planet 2. You go from a planet closer to the sun to a planet further away from the sun. That would be your Earth-Mars typical situation. If you do that, it means that you have planet 2, your destination, that has its heliocentric velocity with respect to the sun, denoted by V2, say in this direction. Okay, the sun is here, the planet is riding along its circular orbit like that. Because you are entering or you are approaching this planet from the elliptical transfer orbit at its apogee, right? You go from low to high, meaning that you are now at the apogee of your transfer orbit. That was a green orbit in the heliocentric perspective I had drawn before. It means that the speed you're going to have with respect to the sun is going to be less than the heliocentric speed of the planet around the sun, which means that from the planet's perspective, you are slower, or in other words, you are going in the opposite direction than the planet. And that'll be the trajectory you would follow coming in from this direction, because you are traveling with a speed less than the planet's speed with respect to the heliocentric analysis, and therefore from the planet perspective it's as if you are coming towards itself as opposed to away from itself. Okay, it's all about perspective here, right? So if I'm traveling on the highway at 120 kilometers an hour and I'm passing a car on my right which is traveling at 100 kilometers an hour, it's as if that car would be coming towards me from my perspective. So from the perspective of the planet going in that direction at a faster speed than the spacecraft, it's as if the spacecraft would be coming towards the planet, okay? And because this is all done in the planet's perspective, this is why the spacecraft is following this trajectory relative to the planet, coming in the opposite direction. If that's the case, then what's going to happen is that you have some V infinity, let's say, arrival at the planet here, and then you would exit with the same velocity here that we're going to denote V departure, but that's not V departure from the home planet. This is V departure upon exiting the sphere of influence of planet 2. Okay, so you enter the sphere of influence with V infinity arrival and you exit with V infinity departure, and the magnitude of those two vectors are exactly equal to each other, okay? Because you are entering at a distance r infinity and you are exiting with a speed at r equal infinity 2, okay? So in terms of norm, we can say that V infinity departure is equal to V infinity arrival, those two being with respect to the planet's perspective. But there has been a change in direction of this vector coming out and this vector coming inside or arriving at the sphere of influence of planet 2. So although we didn't scale this vector up or down, we nevertheless change its direction, which means that there has to be a delta V involved. Interesting. So I'm going to say because the vector itself, departure, and the vector at arrival are not exactly equal to each other, because although their norm or their magnitude are equal, their direction is not. It means that there must have been a delta V vector involved somewhere, okay? And that delta V is actually coming from the planet itself. So the planet would accelerate the spacecraft. Let me just, I'll mix up the terminology. If it's leading edge or trailing edge, I always get confused. Okay, so this is known as the trailing edge flyby trajectory. So whenever you get this situation that you have trailing edge, meaning that you arrive in the opposite direction in terms of velocity vector with respect to the planet, it means that the velocity that you're going to get at the exit with respect to the sun, v departure with respect to the sun, so capital V that you're going to get out of it is going to be v of the planet with respect to the sun, v2, plus v infinity departure with respect to the planet. So the spacecraft with respect to the sun would have gained some energy. With respect to the planet, it didn't gain anything in terms of speed. It's only when you look at the sun's perspective that you're going to get a spacecraft departing the target planet number 2 with a velocity which is higher than the target planet speed along the sun. By how much? Well, by this much. Okay? This is known as trailing edge trajectory, or widely commonly referred to as a slingshot maneuver, because you are essentially using the planet's energy to boost yourself up into a higher orbit. Okay? And this is how some satellites have been able to go from inner planets in our solar system to higher planets in our solar system just by using the fact that they can be slingshot by using gravitational attraction from one planet to another one. Okay? That's when you go from a low orbit planet to a high orbit planet, but you could also have the other situation when you go from a high orbit planet to a low orbit planet, 1 to 2, meaning that if this is the sun, you now go from here to here. So you come back from Mars to the Earth, for example, and then you would get the total opposite situation where you have planet 1 with its heliocentric velocity, like that. You have enter. You get something like this because you are arriving at the sphere of influence. So that was planet 2. We're always looking at arriving at planet with no delta V maneuver. So this is planet 2, which is closer to the sun. You are entering the sphere of influence of that planet from here. Okay, so that would be V infinity arrival, which notice is now in the same direction as the planet's heliocentric velocity, or velocity with respect to the sun, because the speed you had along this big elliptical transfer orbit upon arriving at planet 2 was higher than the speed of planet 2 with respect to the sun. Okay, and then what's going to happen is that it's going to do, the planet's going to turn this velocity such that V infinity departure, if you just let yourself coast, is going to be at a different angle. And again, that means that although the norm of this one is equal to the norm of that one, there is going to be a delta V maneuver being applied. And this is done using the energy of the planet, if you will. That's one way to conceptualize it. But this time, you're going to exit with a speed with respect to the sun, which is going to be lower than the speed of the planet around the sun because you are going in opposite direction upon exiting the sphere of influence, which means that the departure of the spacecraft with respect to the sun is going to be v of the planet with respect to the sun minus the infinity departure. Okay? So you are exiting the planet with a lower velocity than you had before, or you are essentially braking yourself freely without having to open thrusters and apply a retrograde propulsive maneuver. So those are two benefits of doing flyby trajectories, either to boost yourself into a higher energy orbit than the planet you are targeting, or braking yourself and kicking yourself into a lower energy orbit than the planet you are targeting. And all this is coming with no propulsive maneuvers involved, only using the energy of the planet. So essentially here, you are effectively slowing the planet a little bit, whereas here, it's the opposite. But because planets versus spacecraft is like infinity compared to zero in terms of mass, we don't see the effect of a planet slowing down because spacecraft is boosting its energy up. That's not how it works, okay? But that's the basic idea behind flyby trajectories upon arriving at planet, yet applying no delta V maneuvers to keep orbiting the planet, just letting ourselves coast and letting gravity of the planet turning our speed vector or velocity vector with respect to the planet and essentially boosting or decreasing our net energy with respect to the sun. Okay? This is known as the flyby or slingshot maneuver that you've heard quite often in literatures, textbook, or science fiction books, or even in TV shows or movies. Okay? So this effectively concludes chapter 4, which was all about orbital maneuvers. Next time around, we're going to dive into my most favorite chapter of all chapters involved in this course, which is spacecraft formation flying, where the objective will be to derive the equations of motion of a spacecraft, this time not with respect to the planet, but with respect to another spacecraft orbiting in close vicinity to spacecraft 1, such that we could obtain the relative motion between those two objects orbiting around a primary body. So that will be up next time. Till then, keep safe and see you next time.